going on, folks? It's Mike here, and welcome back to my Modern C++ series. In today's episode, I bring to you a very special guest lecture, none other than by Bjarne Stroustrup, who's going to be talking about concept-based generic programming. And in this lecture, you're going to learn about some of the things we've been talking about on this channel recently with C++ and safety. So he's going to be talking about using constraints or some of the concept-based stuff that we've learned about earlier throughout this talk, and he does a really nice job explaining how to use some of these different tools that we've also seen on this channel and that you can start putting into practice as an example. So this is part of a guest lecture at Yale University in which Bjrane took an hour and a half or so of his time here to give us some knowledge on concept-based generic programming. So with that said, thank you again, Bjrane, and here is the lecture. All right, folks, I think we're about time here to get started. So thanks, everybody, for joining us for our computer science colloquium. We're very honored today to have Bjarne Stroustrup with us, visiting from Columbia University. He doesn't need too much of an introduction, the creator of the C++ programming language. And today he's going to be talking to us about generic-based programming with concepts. So Bjrane, thank you so much for honoring us and coming today, and the floor is yours.
Sure. Okay, so I'm going to talk about what is now current generic programming, and I'm going to do it with some examples. Generic programming in C++ started from the very beginning, but the version we have now was done by Alex Stefanov, so there's a couple of books there if you are really into it. So Alex had a nice modest aim there. The most general, most efficient, most flexible representation of concepts. And concepts here means ideas. And he has some rules of thumb which people sometimes forget. Don't abstract for the sake of abstraction. You actually have to have a need to generalize, to make more specific. And abstraction for concrete, efficient algorithms. This is worth saying because some people think that abstraction means bloat and slowness. And I was told once I was going to France never to use the word abstraction because they all knew it meant bloated, complicated messes. And that's not the idea here. And we want to maintain optimal performance. That is, we want to basically beat all other kinds of performance. It's not unambitious. My job here was to actually make it work. Alex couldn't actually build what he wanted. He tried in Lisp, he tried it in Ada, and he couldn't really do it. So I wanted to express things in such a way that the performance and flexibility was maintained, and I wanted to combine concepts, different ideas, as long as it made sense. Things like I wanted a vector of elements, but only if the elements could be elements of the vector. I wanted to sort a container, but only if the container had the properties necessary for doing sorting, and wanted minimal overhead. You can't talk about performance without minimizing the overhead. You have to compare to the sort of the gold standard of it. And I wanted to get generic programming as simple to write as ordinary code because, well, if nothing else, if you look at traditional template metaprogramming, it's far too complicated, and this is part of the idea of getting it better. And I outlined some aims for generic programming in 1994. Actually, before that, this is what you can find in the book, the Design and Evolution of C++, which I wrote up in in 94. So none of this is new. We wanted to be general. That is, I wanted to be able to do more than any individual could think of. A group like us can have more good ideas than any individual in the group. I wanted uncompromised efficiency. Otherwise, the efficiency freaks would write something else that is more complicated, more buggy, harder to maintain. And I wanted statically typed interfaces so that I could verify that my code was reasonable. The way you write large pieces of code is you have good interfaces, otherwise you can't manage it. There was only one problem. At that time, I could do 2 out of 3. Any 2 out of those 3, but not all 3. I spent a very large amount of time traveling around talking to practitioners and academics and such to see if anybody knew how to get all 3. They didn't. And it took us almost 20 years to get to the point where we could do this. And I'm going to give you some example. And there's some further requirement that I also outlined, but not in the exact same place. Basically, it has to be affordable. We shouldn't require people to have really big, expensive, fancy computers or really slow, difficult compilers that also requires big computers. And it has to be teachable. To quote the inventor of object-oriented programming, Christian Nygaard, if we require PhDs from MIT to do it, we have failed. Now, nothing rude about PhDs from MIT, there's nothing wrong with them, but there's a shortage, so if we needed that for all this kind of code, we would have failed. So those were the ideals, and I'll show you how we can do it today. Now, every good design, every good solution starts with a problem. This is not an abstract thing. It is want to build something specific, and I wanted to, in this particular case, for this particular example, I've been annoyed by the rules of C for converting built-in types. You can assign a long to a char, and it's almost always wrong. You can assign a 7.5 to an integer, and you lose the 0.5. It doesn't even round, it truncates. And there's more examples there. New examples have come up, like in AI and graphics, they use floating point numbers where the mantissa is very short, like 6 bits, and to get a larger range from the exponent. So all of these things here gives trouble. I particularly dislike also the mixing of unsigned and signed numbers. If it had been up to me, you couldn't do that implicitly, and you would only use unsigned for bit manipulation. Anyway, I didn't design this. It came about from old C, and I've been looking for ways of dealing with this for a long time. So let's see if we can solve this problem using generic programming. According to Alex, it should be the most flexible, most efficient way of doing things. So let's try. So first we have to discuss arithmetic types. That's where the problems are, and we can now define an arithmetic type. An arithmetic type T is a number. I'm going to deal with numbers, and I'm going to deal with integral types and floating point types. So basically, a thing is considered a number on my program if it's either integral or floating point. And so these are predicates. Basically, this means is it an integral type, and this means is it a floating point type. It may be a slightly unusual notation, but that's a traditional notation for having things based on types in C++. And so that's, I'm going to deal in numbers because that's where the problem is. And then we can look at the definition of arithmetic types and see where narrowing can happen. Narrowing is when a value is converted from one type to another and the value is different. I don't want that. That's what we're trying to solve. And you can actually write this reasonably easily. First of all, we can narrow from T to U like this. First of all, if it's the same type, of course you can't narrow, so it shouldn't be the same type, not same as. And then, and if they're both numbers, we are going to deal with that. And if it's a floating point T and an integral U, then you check whether there's enough digits to represent the integer value. And if it's a signed and an unsigned, you have to check that the signs are different. In those cases, the same. In those cases, the standard says that you might get narrowing. So this is the definition of where the problem can occur. Interestingly enough, it takes a couple of pages in the standard to say that. We are now able to say that in code. It just says, here's the problem. And by the way, these things here called concepts are, as I said, predicates. They are compile time evaluated, and they can take type arguments. So that's what I'm doing here. I've reduced a couple of pages of standard to code that can be understood by us. Take my word for it, that's easier to understand than the standard, and by the compiler. And so we're formalizing this because it's really a mess. Especially the rules for signed integrals and unsigned are a mess. They've been a mess since '72, so they're hard to deal with. So we need to see, what do we do if you can narrow? We want to test whether a value will be narrowed. In other words, the first thing was the type system. Is it possible? Second is, let's look at a particular value to see if it actually will narrow. So first, we are going to what am I doing here? Yeah, we're here. So first I test if it can narrow. If it can't narrow, not can narrow, it returns false. There's no problem. It's nothing we need to do. Otherwise, if it's an unsigned and a signed, then if it's larger than the numeric limits for the signed, there's one bit extra in the unsigned, then it will be true. It will narrow. Strange things happen. Signed integral turns into unsigned and vice versa, and here's vice versa. If context, where if it's an unsigned integral and I'm converting it to a signed integral, we better make sure that it doesn't become negative. And if not, we do something really simple. I convert the one to the other and see if the result is the same. The important thing here is that we are only doing the minimal number of tests. These are, all of this context stuff guarantees that we minimize the number of tests we're going to do. Remember the ideal of being the most efficient. If you just test all of this at runtime, you pay for it a lot. And in real code, these problems rarely happen. People have tested their code. These are very rare. On the other hand, they happen and they are problematic. So here's the test. So we can do it. And so I can now say, if it will narrow the value, then throw an exception. If not, to just do the conversion, because we now know that it will not change the value. And not everybody likes exceptions as much as I do, but remember that this is very rare in real code because people have tested, people tend to trust the code, and they get the bugs anyway, and so you throw an exception once in a blue moon when you have the problem. That's exactly what exceptions are for, exceptional circumstances. So we can test this kind of stuff, and you can see there's a bunch of tests I test convert to, and see if what the results are. And you look at this and think about real code. Nobody is going to do this, and nobody is going to do it consistently, even if they try. If you've got 1 million lines of code and you have to have every conversion between a signed and an unsigned and a float, then you're not going to do that consistently, and you'll still have the bugs, right? We want to guarantee that the bugs doesn't happen. Also, even if you get it right and everything works, then somebody goes and changes the type from an int to a unsigned, and now the whole testing has to be reevaluated to be good. This is not going to work. So we have a solution. It just doesn't work in the real world because of the way people are. So let's make it implicit. Let's define a number as one of these things that doesn't do value changing, narrowing conversions. And so basically what we can construct it, and we test that there's no strange conversion. We can assign, that's initialization, that's assignment. We test that the value actually can be represented as the number we have here, and then we can extract the value. We now have a type which we call number that can handle the arithmetic and floating point numbers and never get a narrowing conversion. That's what we wanted, and we can now write code like this. Here I have a number of unsigned, a number of char, and I can start mixing them up, and I will get an exception if I have done something I shouldn't, and only then. And I will test only when it's necessary to test it. So if you have two chars, it doesn't do any testing. It is not one of these runtime tests of everything. So it'll run approximately as fast as if there was no tests. So of course, having arithmetic types, we need to have our arithmetic, and so we can define those. In the standard is a thing called common. The common of two types is if there is a thing you can convert those types to so that they can be manipulated together. That's defined in the language, in the standard library, and this is useful, and you can extend it if you want. You cannot, in general, for two types, see if you can combine them with an add, but you can for the ones we have defined and we understood. And so you do that with the other operations, multiply and divide also. So far, so good. And we really, really want to do things like less than. There is my favorite example of what is wrong. Is -1 less than 2 unsigned? And it isn't, according to the rules of C and C++, because the rule says that first you convert, if you have this mixed arithmetic, first you convert the signed to unsigned, and then you compare, and when you convert that one to unsigned, you get a humongous number. So obviously that's not less than 2. So this is something we want to avoid. So we define operator less than to do a test if they are mixed. Fine. Now, so far the simple test is 42 lines of code. So it's not exactly very complicated, but it does a good job. One thing that I guess I should point out that is that you shouldn't confuse the example for what it is an example of. This is an example of how you can combine compile time evaluation, comparison of types with runtime checks to get a complete, guaranteed and minimal set of runtime tests. This is just an example. You can do that in other areas. Yes, you can do the number of integers, you can combine things like that and get the exception if and only if you make a mistake. Now, one reason I'm looking at this is I was looking at the range errors, and it turns out that almost 70% of all range errors, buffer overflows and such, comes because people mix signed and unsigned, and they get a wrong answer. Here I've made a little mistake. I have an array of max errors, and my finger slipped and I typed. Since I use unsigned there and signed here, there's a conversion of 500 to unsigned, and you get a very large number here. Unfortunate. So you are now, if you are trying to do checking with a span, then you're never going to get an error. A span, by the way, is a standard library type that says we start here and there's n elements over there. That's all there is to it. And if you use the right implementation, which comes from the core guidelines library, you will get an exception if you overflow. This one will not appears to work and catch errors, but it doesn't. And this is one thing that happens a lot in code. Actually, it doesn't happen that often, but out of the errors that happens, it's a large number. And this was why I wanted to eliminate them. So let's eliminate the range errors while we're at it. Now we have the basics for doing it. So first I define spannable. That's something I can have a span on, right? And there actually is some in the standard library. It's called ranges, contiguous range. Okay. Anyway, I can extend spannable. I can't extend the standard library easily, so I give it a name. It's also shorter. I'm a bad typist. So we say what is spannable, and I can now define a type span that does things properly, more than the standard span. So basically I have the lower level abstraction here, a pointer and an unsigned, and then I have a check function that checks that it is in range, and here I make the spannable, and I take the data and the size of the spannable, because that's to be spannable you have to have a data and a size. It's in the standard. And I have a subscript, and the subscript I give it a number, not just a plain unsigned, but one of my numbers that check when you do conversions. And now I can do the check here, and we now know that this thing here has the right value. It has not been converted to something that eliminates the span version. Okay, and I can now write code like this. I have a couple of arrays there. I try to make an array out of a negative number that's going to be caught. Of course you wouldn't write that, but you might very well write a span of n, where n was a result of a mixed signed and unsigned value, and you got something you didn't expect, and your checking will never work. Here I do the span of, what have I got here? A span of a vector of doubles. It's okay if 10 is in range here. I don't know if the 10 is in range, but when I create the span, I check. And here, -1, it'll throw. And here's a more realistic example. I make a span of an array. Where was that array? This looks like a bug. There should be a single A. And then integer, the integer, and here comes the realistic thing. That is, I'm subscripting with a value I got out of somewhere else. The minute you don't have a constant here, the minute you don't have a single variable here, it comes as a result of a computation, and it can have an error. And most errors that happens either in a place like here, where I don't know if there's 10 elements, and I need to check, and it does check. And here, where it's a result of a computation, and that's the places where errors happen, and they'll be caught now. Okay, now, if you look at that, I'm repeating a lot of stuff. Why do I have to say that it's a span of doubles when it's a vector of doubles? Obviously, it has the same element type. So let's deduce these things, and we can do that. We say that if a spannable is a span of R, then we make a span of the element type of what the range is, value type is. I mean, we know that, the compiler knows that. That's the point. And now we can write, there's the integer AA that I used on the previous slide, sorry. Now I can say span of AA, and it deduces it to be a span of integers. See, it says integer right there, and it has 100 elements, so I don't have to say that again. So now, two things are happening. One, I have less to say. Two, since I don't have to say it, I can't get it wrong. The compiler knows it. I'm using the compiler's notion. And these spans can be used to simplify code. here's the write all the elements of the span out using a range 4. So span is a very useful and very simple type. Okay, now this span, so this unfortunately is not a very realistic span. Span is not always of a container. You have spans of parts of a container, and you have to say a span of data you got from somewhere else. So let's start here. This is a difficult one. You have a span, you're giving a pointer, like from the operating system or from an allocator or something like that. But at least you can check that it doesn't have a bad number and set it aside. Here's the span of 0 to n. Here's the span of low to high. This is fine. The point here is that the span of a pointer now stands out like a sore thumb for static analyzers and for humans doing code reviews, and the others are guaranteed to be correct. So we have isolated what can be checked and done, and what cannot be checked, so that people can find it and fix it. And to get this to work, we need some more type deduction. So here's the simplest one. A span of t stars, of course, is a span of t's. You initialize it with a pointer to a t, so the elements are t, and here comes the other versions of type deduction. More realistic. Now we can test this, and it goes down, and the point down here, that one is unchecked, but it's now reasonably obvious and can be found by an easy static analyzer or a human. There is an out of range one, it'll throw. Fine. We've dealt with this. Now, given that we use the compiler's information to shorten our code and make it less error prone, the number starts getting complicated. Why do I have to say number of unsigned, things like that? So what I can do here is I can say, if I have a number of an initializer, it's a number of the type of the initializer. That's just what we want. So if now have a number initialized to 1, it's a number of integer. Number of an unsigned is number of unsigned. Number of double is a number of doubles. Now we only have to say number of type if the thing is different from the initializer. And by the way, my rule of thumb is always initialize your variables, otherwise you are opening yourself to trouble. So basically, we now have to be verbose only there. And that means that now looks very, very much like ordinary C code. We're notationally basically identical. Before I go further, I'll just point out that none of what I've shown you is classical generic programming, because in the old days when we had just templates, we couldn't do this. What you need is concepts. You need to be able to define properties of types and test on them. So this is demonstrating the solution to something that has been standing as a problem for about 20 years, and now the solution is fairly simple. It may look unusual to you if it's the first time you see it, but it's really quite simple. If you can't understand the first 42 lines of code, maybe you have the wrong job. Okay, let's go back and look at the traditional stuff and see how that improves. So here's the classic sort. We sort a type, which we call random access iterator, and it has a first and a last. And the first and last has to be type random access iterator, and the standard precisely says what is required for first and last. Random access iterator must be a pointer-like type to something that can be used to iterate over a range of elements. It must provide random access to that range. The elements must be comparable with less than, and the first and the last must define a range. This says so in the standard. There's nothing here that tells the reader of that code what it is. There's nothing here that tells the compiler that these rules here has to be obeyed. It just says there has to be a type, and we have two elements of them. So we have not been precise. It's violating the rule that I set up front, that we have to precisely specify what we are doing. So this has bothered me for a long time. So the code was spectacularly successful. I mean, even good, sensible people used it despite its problems. It is efficient, it is flexible, and it gives awful error messages. If you have used this kind of stuff, if you've been using generic programming in C++, if you've been using template metaprogramming, you have had pages and pages and pages of error messages that are just about incomprehensible. It's not your fault, but I couldn't do the design. None of the experts could do the design back when I tried first, so I had to choose it. So what have we got here? Let's see. Here I'm sorting a vector. Here I'm sorting a span of strings. This is fine. This is what it does well. And here I try to sort a list. Lists don't have random access. So here it gives an awful error message because I didn't precisely define what sort was. Okay, so let's do that. So here I'm saying that I need a random access type, random access iterator type. I want a predicate that says less than, and I want to be able to sort it with that iterator and that predicate. That's defined in the standard. Sortable means that you can compare using the predicate. It means that you have to have random access. It double checks. It says that it must be able to swap elements, because that's what you're doing with sorting and things like that. That's defined in the standard. There's libraries in the standard so that you don't have to write the lowest level of concepts. This is just like you don't have to write the lowest level of functions when you write code. I mean, when did you last define a square root of double? I mean, in my case, I had a course about it in my undergraduate studies, and I wouldn't do it again because I'm not the expert in floating point numbers in any way. This has been good enough for many years, so why would I do that? The standard gives you things like sortable to do it. So I want to sort that range with that predicate, and this is what the standard says. Fine. Now the compiler knows it, and you can read it if you like. You probably won't, because you'll trust it. It's a standard, and it's in the standard library. Anyway, it still doesn't quite do things. It's first of all, the old style works. It is just checked at compile time. So we have compatibility. The code you wrote 25 years ago still runs. If it was correct, it runs well. If it was wrong, you get a decent error message instead of an appalling error message, but I don't see why it wouldn't work if you used it for 25 years. And so you can do the old stuff, and we can do the new stuff with a predicate, and the only difference is that if you try to sort the list, it will now say the list doesn't provide random access. The error messages are not as good as they could be. They're actually not as good as they were for my experimental implementation of this earlier, but I hope it'll improve. So remaining problems here. A pair of iterators is supposed to specify a range. These things have been seen in the wild. Vector of n to vector of begin. Somebody did some cut and pasting and got it backwards. This is not a hypothetical one. This is one I've been seeing. And then here we begin one container and end another container. This is pretty disastrous, so we need to get rid of this. And one of the aims of C++ is to allow you to say precisely what you want. I didn't say I wanted to sort a container or sort a range. I said I wanted to sort something in between two iterators. It's not only verbose, it's not precise. So let's define there's a there's a sortable range. It's a range, random access range. I said it had to be random access. It has to be a range. A range checks that it is something that is like that, either begin end or begin size or something like that. And it is sortable with the ranges iterator and the predicate. So I define a sortable range. Now I have a sortable range, and I can say I want to sort want to sort a range with less, and it has to be sortable. And now I can implement that very easily. I could just implement it with the old stuff. Begin end. And now I can write these things easily. It is now, I no longer have to say VD of begin, comma, VD of end. I can just write the precise and short form of this. So what I've done here is I've slowly used concepts to eliminate the problems of traditional generic programming. You could do something like that before. Several people have done so. But it is very tricky code, and it takes many pages of template metaprogramming. So it also compiles slow. This stuff is fairly trivial. I've shown it to you in, 4 slides? And each slide was half code and half use testing. So we can now say, what would we want to do if we really wanted to sort lists? I mean, this may not be such a great idea to sort a list without saying list, because lists are not a good data structure to sort. They are actually awful for that, because sorting involves traversing and doing things like finding the middle, which is not very good for lists. But anyway, so we define a forward sortable range, which is the same as the sortable range, except that it only requires a forward range. A forward range is one that you can converse from. You can traverse from the beginning to the end, but you can't go backwards to do random access. And then I define my function here that requires a sortable range, and I have to use a slightly different algorithm. There is an algorithm that in the standard library that does a list sort, but I thought I would just do it simply. I create a vector from the range, then I sort the vector and I copy things back again. This is usually good enough, and this shows what you can do in the case where the standard library doesn't have a specialized function for doing it, or if you don't know that function. Okay, and now I can do this. I have a vector, I have a list. I first sort the list. This is standard overloading. Sorting with a forward range can be done for a list. So for a vector. But since the vector version cannot implement that one, we choose that one. For the vector, we can do either of our two functions, but the rule is if the two concepts, the two set of predicates, are subsets of each other, you pick the strictest one, because that's supposedly the better. Why else would you do it stricter? So this one chooses the default, the random access one. That means that you don't have to create class hierarchies or define what types will work for what concept and such. The compiler will pick the right one based on the information you give it, and if these two had overlapped in strange ways that couldn't be resolved, you'll get an ambiguity error. Fine. So the rules for overloading templates based on concepts is far, far simpler than the rules of overloading ordinary types, because they're defined today with all the stuff I have available, not in 1974, where they didn't have all of these. Okay, so one interesting thing about concepts is we've always had them. In C, the built-in types are either arithmetic or floating. That started in 72 or so by Dennis, thanks to Dennis. In the STL, we have iterators, sequences, and containers. Mathematical concepts, monad, group, ring, etc. for a couple of centuries. Graphical concept, edge, vertex, graph, and DAG, we've had them since 1736 when Euler defined them. But I'm just pointing this out because this is part of the reason it's called concepts, and it's also not new. What is new is we can tell it to the compiler so that the compiler can use it, and we can write it down in a formal manner so that we can read it. Okay, so none of this would work unless the programmer, unless the mathematician had these concepts in their mind, but we can write it down. And concepts are compile time functions that can take type arguments. It's simple, general, and we must learn to use them right, just like we had to learn to use functions right. If you teach novices, you'll notice they write just straight lines of code, and instead of defining functions to represent their ideas, we have to learn to do the same. And it's not that hard. Okay, concepts are typically built out of other concepts, just like functions are usually written using other functions. And so here I showed you before how to make the forward range. It uses the standard forward range and the standard sortable concepts. It's just like you write a function. Sometimes we, of course, have to go and use and define the concepts straight from the raw language, just like we write our most basic functions out of the raw language. And so here is a simple example. I want to define what it means to be equality comparable. And we can do that by taking two types and then say if you have one of the one and one of the other, they are comparable, equality comparable, if they can be compared with equals, with non-equals, and we can swap them and do it in the other way around. These things are called use patterns. They were defined by me and Gabidos Reyes back in 2006 or something like that. This is different from a lot of constraint systems that are using class-like things. One of the curious things is that the most functional language that we know of, which is Haskell, uses classes to define type constraints, whereas C++ uses functions. Functions are more general, easier to write, easier to use. Okay, so requires is a low-level mechanism for defining concepts. If you start using it, it's as if you used embedded assembler in your code, so don't do it. Use them for defining concepts. And one reason we need use patterns is that there's many ways of expressing things in C++. So here is some examples of how to express that A can be added to B. A plus B. It could be a function that takes x and y. It could be, I should have said x and a y here, that takes an x and a y. It could be a member function. It could be something relying on implicit conversions, etc., etc. So using use patterns, using concepts, means that we can handle mixed mode arithmetic of different types, and implicit conversions, which most of the systems cannot do for this. I'll just point out here that of course we can handle homogeneous things. If the second type U is the same as is not specified, we just pick the first one, and so we can we can handle things that are just one type. Okay, and here we can test it if we want to. The compiler will test it anyway, but if we are doing debugging, if we are building things up in the first place, we can do it with a static assert. Is int comparable with double? Yes. Is equality comparable int with itself? Of course it is. I hope that you can't do int and string, and you can't. So this can be tested at compile time. We usually throw in a few of these just to test our code, but it's not necessary. This is just being careful. One thing that I've heard is that generic programming was new and not thought of for C++, and it's a special, separate language. It isn't. Uniform treatment of types for scope creation and destruction was there in the first couple of weeks of C++. And without that, we couldn't do generic programming because you would have to deal with types separately. And I'll show some more examples of this. Basically, my ideal is that generic programming is just programming. So here's a test. I have a local variable and I have a unique pointer. And they are created. They are both destroyed here. Things are taken care of. So these types don't actually, you don't have to make them separate. The rules are the same. If you build types out of these, then you don't have to have one set of rules for pointers, one set of rules for built-in types, one way of allocating user-defined types, class objects, one way of having local variables. it's all taken care of by the same rules, and that's important. Here's an example of where that matters. I'm creating a pair of a t and a u. People do that often. I could have done a tuple, but let's stick to pair. And I'm wanting to say that I want to create one pair out of another pair. I want to initialize a t and a u out of a tt and a uu. And I can do that if you can convert the t to a tt and a u to a uu. Done. And so this is fairly standard. If there was different rules for how you created and initialized and had scopes of different functions, this would never work. On the other hand, I noticed that this one had a slight problem. It still had the conversion problems that the built-in types had, and well, I decided I didn't like that. So we can simply say that a pair can be constructed from another pair if you can convert them properly. This one here is a bit shorter than the one that uses only the standard facilities, but it does the checking if checking is needed. And the problem is that I went and defined convert to take arithmetic types. And of course, pairs can be made out of any type, so that will not work. But we have overloading, as I pointed out. So here I simply define an overload version that's used if they are not numbers. And there is some built-in facilities for dealing with some conversions, namely the initialization with curly braces. But basically, I'm saying if it's not a number, I will just convert it and hope it works. I could, of course, define this one more specifically and more carefully, but the point is that you can add the system. The system is open. You can overload, you can provide new functions as you go along. That's the main point here. And one thing that shows that this stuff integrates is that one thing that bothers me a lot, bothered me till at least I solved it, was that there was different ways of organizing code for templates and for ordinary functions. Ordinary functions as header files, and there's the implementation here. And with templates, people put them all in header files, and there was no .c files. And so you have to decide very early on when you organize the code whether it's a template or not. If you change it from a template to a non-template, you have to start rearranging your code to make it conventional. I didn't like that one little bit. But we now have modules. So I can define a module. I want a map printer module. I implement a lot of, I use for the implementation a lot of good stuff, and then I define the function, which I say I'm exporting. That's all that comes out of there. It does not transitively and recursively include everything you used for the implementation. So with this, which is a more modern way of organizing your code, getting more useful, we have now unified the way we store generic code with the way we store non-generic code. Another distinction has disappeared, and you should look up modules. They compile maybe 7, 10, sometimes 100 times faster than header include files, and they don't transitively include everything you use for your implementation. So they're good, but it is not an accident that they work the same for templates as they work for ordinary code. If you want to think about modules, think about it this way. It's a graph with a hash table. So when you export something, it goes into the hash table so that you can look it up. Done. You don't manipulate characters and tokens and such if you implement this properly. We're getting something in C++ 26 called static reflection. This is the only time I'm going to talk about something that is future stuff. On the other hand, you can go in on the web to find the implementation of this static reflection, so it's not science fiction. I love science fiction, but this is a technical talk, so let's make sure that it is such. Basically, static reflection is the ability to ask the compiler just about everything the compiler knows. Notice how much in generic programming we relied on being able to ask the compiler questions about types. I can do that also for values, but I was doing it for types here. Here is a more general version of it. You can look it up, go onto say Godbolt Compiler Explorer and try it out. So it's not science fiction. So one thing that there's a couple of examples there: generating I/O operations, serialization, foreign language calls can be done by asking the compiler all it knows about the types so that you can write these things. By the way, the reason I don't want dynamic reflection like Java is that you get far too much data, often bigger than the code for the program, and you now turn programming into a graph walk with weak type checking, which creates bugs. So we want static reflection only. We want reflection only if we want it, only if we can afford it. So here is an example of something I would like. I would like a data member descriptor that has the name, offset, size. That's a useful data structure to get in some cases. In other cases, I want the set of functions available and such to generate inter-language function calls and such. But let's do this, which is almost the simplest case. And the code for doing that looks like that. So that hat there, double hat, is gain information from the compiler, and the information you get has certain names. There's a library with about a page full of things you can ask it for. But here it says look in the compiler and find, well, the non-static data members of it. Fine, we get that. Then we make an array of the right kind of size, the number we have there, and we call it layout. And then for all the elements there, we initialize the layout of I with the identifier, the offset, and the size. And then we return the layout. Again, probably unfamiliar to you, but it's not really that complicated. It's one page, and it's using a library, and you can go and experiment with it if you want to. And so here I take a structure X with some elements, and I'm simply saying get the layout, and it comes from there, and we now have an array of data members with these kinds of values. The strings, they are not really strings because we're not creating objects. They sit in the compiler, so we just say look at it in the compiler. They're constants and they're string views as it is. But the point here that I'm trying to make is this is perfectly ordinary code. I mean, you could argue that this is complicated. But once I've made it, it is just a much simpler implementation of the idea. People usually do things like that with macros and lots of complicated stuff. Here, it's a perfectly ordinary library call of a library you made, and you don't need anything special to use one of these things, whereas you probably need something special to learn how to do it. That takes some time, but you know, this is C++ 26 and it's still 25, so we have time. So the major concept design decisions, concepts of functions. Concept can be partial constraints and so on. I'll just show you the examples here. There are functions for flexibility, generality, use patterns are good. Multiple arguments, that means we can create constraints that involves multiple arguments. I mean, after all, if you have a function that takes two different types, there should be some connection between those types. If there's not, why are they one function? We can do that. A lot of constraint systems can't do that. And they can take value arguments, so I can I can create requirements of a buffer of being big enough and things like that. There's the buffer example, and requires a buffer of space, and space is defined up here, buffer space. It has to be at least 1k and to be a power of 2, and now I can make a buffer of that, and I can try and use it. Find error, that buffer is too small, that size is not binary, this one is the right kind of stuff. So this is, I said it should be very flexible, and it is. In case you wonder, is power of 2 can be calculated like that. This is a nice little non-test function, so it's very efficient. And of course, it is const eval. I'm requiring that it should be calculated at compile time because, well, it's being used here to constrain declarations. I was asked whether generic programming was better than object-oriented programming. And my claim is that there's overlap in their use, but they are not the same, and it's not that the one is better than the other for everything. They are complementary, and so there's a list there. Basically, we tend to look at classical object or defining types of objects in class hierarchies. With generic programming, we focus on functions, requirements of arguments, relationship between multiple arguments, and here one object of a time. You can go through that full list and check it, but they are not the same, and there are things that you can do in the one and not in the other. So generic programming doesn't offer ABI interfaces, and it only works for the set of types that are available when you compile. Object-oriented programming is open and can be used for ABIs. That's different. Here's an example. This is the classical object-oriented program that I got from Christian Nygaard and has been used forever after. Here, draw all of drawable range R and go through and do the example of draw. I mean, is this object-oriented? Of course it is. It can use a class hierarchy. It is the classical object-oriented program. Is it generic? Obviously it is. It's a generic function. It uses this, but it's more general than you could do in either way. Drawable range requires that you can draw something, and it's defined like that. But that means that I can use classical object-oriented hierarchies. It's fine. But I can also use any type that has a draw function that can be called through a arrow. It doesn't even have to be a pointer. I can just define it. So it's a generalization of both generic programming and object-oriented programming because it can do the best of both. Here, concept can be partial constraint. We found very often that when we start writing concepts, we don't get them right the first time. We don't get them complete. But a concept like this catches most errors. Not all, because it hasn't actually tested whether you can copy it and things like that. But the compiler will tell you when you are doing something that happened. And in general, everything is caught. It's just a matter of where. Generic programming, template programming, is type safe. It's just that it tests too late. Here we move testing up front, and if we don't move it all up front, so what? We'll fix it later until we get it perfect. Debugging is important. And false lookups are avoided. I mean, what's the chance that this will be something different from a number? People have been worrying about that from a theoretical point of view for a long time. And we do have examples where you have two types that differ only in semantics. In that case, we just add a syntax change, like a forward iterator differs from input iterator. In that the forward iterator allowed traversal, we just add an indicator to say what it is, so we can now choose it. And then finally, I and just about everybody else believed that when we'd formalized constraints on generic code, we would have to define and test generic code in isolation. You should be able to compile it in isolation. The problem is, if you do that, you get a lot of indirect function calls in the normal implementation. Also, we get a problem in industrial code. Here, I have an advance, which is in a standard library function, simplified. I want to go n elements along the iterator. Now, I want to log whether I do that. And I want to use the most efficient implementation of this. Now, an input iterator does not have a log function. Can I call this one? There's no indication here. I cannot compile this function if I allow the log. But in most industrial code and most critical industrial code, we have logging, we have debug aids, we have telemetry, we have statistics gathering, you name it. So if we can't do that, a lot of industrial code will not work. And the input iterator doesn't require plus equals, so we can't do that. But there's a lot of code that will do it. So if you advance something that has an input iterator for a vector, well, the vector has it. So is it allowed to use that information? And since the first days of the STL that Alex defined, this has worked. So if we implemented separate compilation of template functions, it would break a lot of code. So these days, this will work, and if you get it wrong, it'll be caught late in the compilation, get a bad error message, but it will not pass as an error into runtime, and we will not do separate compilation of functions because that harms code. So the summary here, generic programming is just programming. The most general, most efficient, most flexible representation of concepts. I can quote Alex Stefanov, and it's close enough. The concepts are compile time functions, And basically what happens here is that generic programming using concept enables us to extend the C++ type system on top of what is provided by the language itself, with a combination of compile time checking, runtime checking, very flexible and minimal cost. So that's what it does. And there's a whole bunch of references that you can look at. And here's the written version of this talk, because I'm sure I went a bit fast at times. So you can read up on it. Okay, questions?
Let's thank the speaker. Yeah, folks have questions, feel free to raise your hand. If some of you have to leave, no worries. We've got about till 5:30 in the classroom otherwise. Yep.
Sometimes we have tricks where we need to kind of abuse the types. Like the one that comes to mind is like the fast inverse square root, where converting the float to like an integer, which would be like back, but it's like being done in a way to approximate the.
If you want to do something different, do something different. You just don't use my safe version. You just use the built-in stuff. It's like sometimes you do want to use unsigned for arithmetic. That's what the cyber guys are doing for their algorithms. They want modular arithmetic. Most of the time, modular arithmetic, if it happens, is a bug. But if you are doing that kind of work, you just don't use the checked version. One of the things here is that this is something you use if you want to use it. It is not me coming to say, I have here a language that defines what is right and what is safe, and if you don't like it, that's your problem. No, that's not what we're saying. We're saying if you like something, you can use it. If you want something else, you can build it. There's nothing here that is not in the compiler for you to use.
I guess a quick follow-on is like, can it be like if I want it for everything else in my project, but I want to be able to do this trick or this abuse of the system,
Yeah.
can I step aside just for that?
You need something else. I mean, you can, of course, not step aside when you're using it, but you can find a way of stepping aside to use the facilities. I'm building something called profiles that is meant to allow you to say, I want this set of guarantees for this piece of code. And it has a facility that says suppress. And if you are using something like this consistently, you would say suppress, then use the standard types and get over with it. Notice also I used standard types inside the implementation of span. If you had a guarantee that says I will always use the guarantee, then I would have to suppress there. But I didn't. That's
You mentioned when we were talking about sorting lists, we would have two algorithms for sorting a vector, but then the compiler would choose the version for the more restrictive type. And this would be done to avoid creating a hierarchy. But how would we know what the more restrictive type is without having a hierarchy to begin with?
Oh, that's very easy. See, I define a concept is a predicate. And so, if this one requires 5 predicates and this one is a subset, these 3, and not that one, the assumption is that if you have more constraints, it is preferable. So if it's like this, you will pick the one with the constraint. If they're like this, they're not subset of each other. There's no way we could choose. And so you'll have to do something else. You cannot implicitly pick it. And I guess you can be specific. One thing that makes generic programming more flexible than object-oriented programming is these hierarchies that you have to build in object-oriented programming, and that's hard. I've tried several times to define a class hierarchy of containers, and I have never managed to have a good one because there's too many differences. Like the ideal set of list functions and the ideal set of vector functions are not the same, which means that I would have to use a union of them and then throw exceptions for the cases where I didn't want to use them, and that's ugly. So, yeah, this is more flexible.